All right, let's start working through our review, page 21. Okay, first step, approaching real number, the right substitution. So 0 for x, we get root 2 minus root 2 over 0. So 0 over 0, we know that this indicates to us there's a hole in the graph. But the limit does exist. We just have to find the hole, remove it, so that we can reevaluate it and find the true limit. We see radicals here, so let's attempt our conjugate method. Morning. Good morning. Expand the numerator. Leave the denominator unchanged. Those cancel out, the x's pair up, so they cancel out as well. Now we can reevaluate our limit. Replace any remaining x's with 0, and we shouldn't get 0 over 0 anymore now that the hole has been removed. So 1 root 2 plus 1 root 2 equals 2 root 2. Number 2, for x doesn't equal to 4, the function is equal to x squared plus x minus 20 all over x minus 4, what value should be assigned to h of 4 to make h of x continuous at x equals 4. So it's kind of like that piecewise function that we've been dealing with, where we're looking for that missing k value. So same idea here. So let me rewrite h of x that way. No, it's the same idea. It's just written out with words rather than function notation. But we're trying to find what h of 4 is that will make this continuous so that everything will pass. So we're just going to walk through continuity conditions and just solve for k. There's no less than, greater than. That doesn't equal to contains both less than, greater than. So all we need is one limit statement for our function. Direct substitution, we do get 0 over 0. We're going. No, because the factoring problem here. Multiplies to be negative 20, adds it to be 1. 5 and negative 4. Reevaluate. 4 plus 5 is 9. Okay, so we keep going. We haven't solved for k yet, but now we're about to, because we're looking back at our first two conditions and we want everything to pass. So that's going to force us to set k equal to 9. And then we have our answer. Any questions? Okay, number 3. Given our piecewise function, find the value of k. That'll make the function continuous. So same idea here. We're just going to go through continuity conditions and solve for k. F of 0, first piecewise. Second condition, limits. We do need one-sided limits here. So approaching 0 from the left, we'll use the top one. Approaching 0 from the right, we use the second one. So 0 from the left, I use the first piecewise. 0 from the right, I use the second piecewise. I replace all the x's with 0. And I got negative 2 from one side, k from the other. And we need one side limits to be in agreement if we want continuity. So we're just going to set them equal to each other, and there we have our K value. And because we're just using continuity conditions as a problem-solving tool, we're not having to go through anymore. You're just using that formula to help you to solve for K. After you solve for K, you can stop. You don't have to produce any justifications. Number 4, we're going to omit, but I'm going to put in another IBT problem in this space. Let's do number 5 first, and we'll come back. We'll call this 5B. So we can take advantage of the space there. But number 5, let f be a continuous function. What is the least number of solutions does the equation f of x equals 1/2 have on this closed interval? So I think if we just sketch this graph out, we can convince ourselves, right? We're going to connect all the dots, and how many times is the graph going to have to cross y equals 1/2 if we connect all the dots? So we'll just plot all these order pairs here. So 1, -2. 2, 3. 3, 1. 5, -5. And 8, 7. And I want to, and here's my y equals 1/2. So I'm going to put a dotted line here at y equals 1/2. So we just want to see how many times does the graph have to pass that point, have to pass that y value. And we've established function is continuous, so I got to connect all the dots here. So go through here. There could be more than that, but it has to be at least how many times? So based off of the graph, how many times does the curve have to cross that y value of 1/2? 3 times, yeah. And this is indirectly using IBT because we can guarantee that spot because we have 1 point below and above our target 1/2. We can guarantee that spot because we have a point above and below our target. We can guarantee that spot because we have a point below and above our 1/2.
You have to graph that, or can you just like look?
Yeah, no, you don't have to graph it. It's just easier for me to demonstrate it. Let's call this 5B here. In this space that we've omitted. This is a more traditional IVT problem. So does IVT apply? Our function is a polynomial, so there's no variable in the denominator to worry about discontinuity. So there's no potential issues that can cause continuity to fail. So we have to make our statements. Next up, plug in your endpoints. And we know what we're after, right? Here's our target y value of 1. We want one value to be below 1 and the other y value to be above 1. Doesn't matter which one is which, we just need one of each. there's -4. That's a number below. So we're hoping that 3 will produce a value above. And we get it, right? We start off below 1 at -4, and we rise up all the way to y value 4. And in this path, it's got to pass through y value of 1 at least once. So we can say by IVT, part B, find the C value. So just set them equal to each other and solve for X. We know square root of 9 is 3, right? So square root of 6 is going to be less than 3. But greater than 2, because square root of 4 is 2. So between 2 and 3. So it's like 2 point something. And we know 2 point something is fine, but then the negative root 6 will be outside the interval. So we're only going to keep root 6. Any questions, page 21? All right, page 22. We're just reading our graph here, approaching -3. It's hard to read here. -3 from the left side of -3. Take a point to the left of -3, follow the arrow. The arrow is leading you to a y value of 3. Part B, approaching -3 from the right side of -3. So now pick a point slightly to the right side of -3. Follow that path. It's also taking me to 3. Limit as x approaches -3 in total. So this is the full limit. The full limit does exist because both points are giving me arrows headed towards that same y value. Approaching 1 from the left. So maybe it's hard to see here. This graph is meant to extend all the way to that hole there. So pick a point to the left of -1. It's headed towards that hole. It's holding steady at that y value of +1. Approaching -1 from the right side of -1. Take a point to the right of -1. Head towards that graph. That point is that arrow is headed towards a y value of 2. Now, if I want to find the full limit, we can definitely tell by the graph that there's a jump discontinuity. We can always also confirm with our one-sided limit that the limit doesn't exist. Okay, use continuity conditions to show that the function is, whether it's continuous or not, at x equals 1. So we're just going to walk through our conditions here. So f of 1, by looking at the graph, it's all the way down here at -5. Second statement, we can obviously tell that if I pick points on either side of 1, the graph is headed towards a limit of 2. So we just make that statement. Sorry, 2. And then we keep going. We haven't failed the condition yet. The third condition will fail because these two are not in agreement. So we want to use indications of function notation and limit notation. So we can conclude removable discontinuity. At x equals 1. Number 7, we're back to solving for k. We're just going to walk through continuity conditions. G. All right, number 8. Number 8 is basically just like 2 separate problems. So we'll treat them like 2 separate problems here. Okay, first things first, direct substitution, 3 in for x. (12/0). This is very telling. We know that there must be a vertical asymptote here. Normally, you would say that the limit doesn't exist. But we can't say limit doesn't exist because now we look, this is not asking for a full limit. It's only asking for how the graph is looking like as we approach that asymptote from the right side. So if there's that back x equals 3, we should want to know how the graph is behaving. Is it doing this? Or is it doing this? And because we're down to 2 options, now we can test what? Decimal. Yeah.
How do you do like 3.1 and we do like 100 or negative?
Right. So if we're approaching infinity and after you compare degrees, you realize the top is higher than the bottom, then you can test 100 or negative 100. But if you get a vertical asymptote and it's a one-sided limit, then you want to choose a number close to that number from either side of that vertical asymptote. So then you use decimals. Right, 3.1 then for x. Numerator, I get positive. Denominator, I get negative, right? 3 minus 3.1 is negative, so positive over negative is negative. So we know the graph is looking more like that, that as it approaches the asymptote, it's going to hang down and go down towards negative. Okay, part B. That's true. So part B, now we're approaching infinity. So what's our first step if we're approaching infinity? Yeah, compare degrees, right? So right now it's kind of hard to tell because there's parentheses getting in the way. So we do probably need to expand out a little bit, enough so that we can pick out the highest degree and the coefficients. You don't have to expand all the way, just enough with the highest degrees to produce what you want to see. Only these values are going to matter. The degrees match, so therefore my limit is what? Yeah, ratio of coefficients, so 3/1, which is 3. So answer choice D. Page what? Page 6. Okay, so this is page number 6, right? So this is, think of A and B as like 2 separate problems here. So let me create, I was kind of packing a lot of things into one problem. Let me separate some things a little bit here. And then separately, f of x is also this. So think of it as, okay, there's one scenario involving 5, another scenario involving -5. Just think of it as two separate problems. So we'll just work through the scenario for A, work through scenario for B, and see if we can mine those two information alone. But for part A, okay, our lines x equals 5 and x equals -5 vertical asymptotes. Well, if we factor everything out, we should be able to tell. So for part A, we'll do. Multiplies be 10, adds to be -7, so -5 and -2. And the 5s cancel out. X minus 5 cancels out. So you know there's a hole at x equals 5, and then you know there's a vertical asymptote at x equals -5. Part B, identify all horizontal asymptotes. You know horizontal asymptotes are end behavior. So to find horizontal asymptotes, we're going to find the limit as x approaches infinity or -infinity, doesn't matter. Yep, and if we're approaching infinity, you know that you're not plugging anything in. Your first step is always comparing degrees. My degrees match, so ratio of the coefficients 1/1.
The denominator slope or higher again.
Right. If the denominator is higher, guess what's going to happen? Let's do that one. Yeah, we haven't done as many of those. Let's say it was this scenario. Approaching infinity, my degree, compare degrees, my denominator is higher. Therefore, my limit is what? Yeah, this is the easiest scenario here. Also, think of it this way: if you forget this rule, you can just imagine, okay, what's going to happen to this fraction as we approach infinity? They're both headed towards infinity, but which side is growing faster? Bottom. So if you imagine the denominator getting larger faster than the numerator, you expect that fraction to get smaller. So hopefully that reasoning will lead you to 0. So part C, is there a value of D that makes the function continuous at x equals 5? Now we know that there is a vertical asymptote, hole at 5. So yes, we should be able to solve for A and allow it to work. But at -5, that's an issue, right? We already know there's vertical asymptote. If there's vertical asymptote, then it's a jump discontinuity. It is not a removable discontinuity. We can't find just a number to plug in something that is a vertical asymptote. So we can only figure out A. We're not able to solve for B because that's a vertical asymptote. And we confirmed it with looking at part A. So for part C, I'm just going to walk through and solve for A.
The test, do we have to go back through? We have to go back through this whole thing, or if we just plug in x minus 2 or x plus 5 and then plug in 5. Do you want it, or do you want us to show it again?
Oh, you mean rewriting these expressions?
We have to rewrite the entire expression, show that we found the hole again, or can we just
Oh, you mean like jump directly, with
Yeah.
the, remove that and just go directly here? You mean?
Yeah.
That's fine. But I do want to see that you're testing that 0 for 0 before you go any further. Yes, yeah, 3/10. Okay, so for C, yes, we do have an A value. And then for D, no, because vertical asymptote at x equals -5.
There's non-removable discontinuity of x equals negative.
Yeah, that's fine. Yep. No, because there's no removable discontinuity at x equals -5. Yep, good. Okay, all right, back to page 20. One, 22. Number 9, limit problem. The right substitution first. Three times 3 is 9. Square root times square root becomes just the x plus 9. Square root goes away, but we do need to replace that radical with a set of parentheses because there's that minus sign that needs to distribute. This becomes 9 minus x minus 9. 9's cancel out. I'm just left with negative x. So negative x over an x. X's cancel out. There's a -1 left up top. Reevaluate your limit. 0 in for x. 0 plus 9 is 9. Root 9 is 3. 3 plus 3 is 6. But that goes in the denominator with a -1 up top. So -1 over 6.
You want us to write D and E and then with a subcategory of like negative infinity, or can we just write negative infinity? I know on the quiz we were doing D and E and then the sub. That's one of the.
You mean if there's a vertical asymptote? Okay. I think, yeah, I think in the instructions, it will say if the limit does not exist, provide additional information if possible. So if that's the case, if there's a subcategory, then if this will be thing infinity and this will be positive. All right. Any questions before we look at number 9? All right. So here's number 9. These A and J are end behaviors. So this is what the arrow is doing as it exits from view. So as we head left, the graph is going to go down. So we know our graph is going to do something like this as it exits. And for J, as we approach positivity, it is going to flatten out at -2. So there's a horizontal asymptote at y equals -2. But my suggestion is, if you know there's a horizontal asymptote, just put a dotted line at the edge of the graph so that it doesn't throw you off seeing that dotted line extend all the way across, since it's not going to matter. All right, I'm going to fill in the rest of it here. So with limits, I like to do holes and they extend from both sides. This is just approaching -4 from the left side of -4. Or from the right side of -4. I'm going to just force this to be an endpoint that feels easier to me. Just don't pick it up at the other side here. 3 from the right. Six, 3. Any questions? Let me just create a few problems for us to practice, some additional problems for us to practice. Grab a scratch sheet or any open space you can find. Direct substitution first. If you get 0 over 0, then you can focus on what to do with that numerator to merge it into one fraction. And so my work was mainly just focusing on this, trying to get it down to one fraction. Once it's down to one fraction, now I can multiply by the reciprocal in hopes of pairing and canceling out the wholes. But this divided by x, the same thing as this multiplied by the reciprocal of x. The reciprocal of x is 1 over x. The whole has been removed. Reevaluate the limit, plug 0 into the remaining x. 4 times -4 is -16. It's in the denominator, so -1 over 16. Nine to the x divided by x to the 8th minus 5x to the 9th plus 4. Well, this is what comparative growth rates, right? Which side is growing faster? You got exponential divided by polynomial, which means that it's either doing this or it's doing this. Right? It's growing without bound, increase or decreasing without bound here. So what can we do? Between
Put 100.
test 100. Numerator we get positive, denominator we get negative. Why negative?
Because the negative or the root 9, it's a great number and it's not even making it negative.
Yeah, so these are both growing fast, but this is growing even faster. So this minus number larger than x to the 8th is going to force that negative.
At 9,000.
Mhm. Okay, what do you see?
Denominator.
Yeah. Logs versus radicals. Radicals is eventually will catch up and overtake the numerator. This fraction is getting smaller and smaller, so 0.
What's the like order?
Yeah, so it's L, R, P, E. Logs is slowest, radicals is next, polynomial, and then exponential is fastest.
Take the test during third period because I'm gonna go out today. Second.
Sounds good, thanks. Okay, what do you do if we see infinity? Degrees. What do you know about degrees? Bottom is higher, right? If I were to fold this out, this would be x to the fourth, x squared. I still get x to the sixth here. The highest it gets is x to the sixth. My denominator is higher, so gotta go to 0.
How do you know if you're comparing like the growth rates or if you're doing like horizontal asymptotes?
Good question. These are both under the same family. These are both kind of like polynomial algebraic. So you only do comparative growth rates if these are completely different families of functions. It's like logs over polynomial, or radicals over logs, or polynomial over exponential. But these are different. Yeah, this 9 to the x is exponential. And then x to the 8th, that's polynomial. So these are different. These are different. And if they're the same, then you go to compare your degrees. Yeah. How many asymptotes do you expect for number 10? This is one of those strange ones, right? This is 2 asymptotes. So once you find the ratio, just change the sign to get the other one. Okay, any other questions? Right, let me know if you have individual questions for me.
I think that I was gonna do a cancel solving for the test.
I'm sorry?
What I was gonna do, a cancel solving for the test. 6 weeks. I said a couple days ago that I was gonna do it. I'll be at dinner time, but it got me told.
Oh, that was my thing. Okay.
6 okay.
So if you're approaching 70, it's graded. Yeah.
So when I'm like, yeah, column and like the numerator's greater, that's when I like. Okay, thank you.
Yeah, it's easy to understand. The interviews IBT.
Yeah,
This one here.
Okay, so that's my question. So like the way we said, if I just say like by IBT or I have to show this, right? I have to.
Yeah.
Somehow, yeah. Okay. You can do it in multiple, you can do it in longer statements, but this is the way I present it, it's so simple. Yeah, it's the most efficient to get all the information across. But do I have to say there must be where C, kind of like F, T, or zero? Yeah, that's fine. That's fine, okay. You can say F equals 0 on A0. Okay, thank you. And you have to do like it's continuous. Yeah, somewhere, I have to see the statement, somewhere, if I think it's in the past, I gotta see that somewhere. Yeah. Thank you. Yeah.
Let me know how it goes.
It's fine, so you just say equal to 0. Yeah, whatever that number is, set that equal to the function. And then bring everything over to one side, factor it on the other.
So you know it's continuous by plugging in the, what's it called?
Well, you know it's continuous because there's no denominator variable that's causing most of this. If there were, polar asymptotes, then you have to set that equal to 0 and see if it interferes. This one wouldn't interfere. It goes divided by x minus 1. There's a discontinuity at x equals 1, and that's going to interfere. That interferes with the interval we saw function was not continuous. I think that's fine.
Thank you.
Mr. Rankin, am I still good to come in half of third?
That's right, yeah,
Okay.
come halfway through third, and I'll give you a test. You sit
Okay.
back and you start it.
Okay, I sit in this row, so I don't know if you're gonna like, give it a specific row, but I sit in this row.
Okay,
So then like afterwards,
Right.
go back to my seat
Appreciate
so that there's no like,
got it.
yeah.
Thank you,
Okay.
thank you.
Yeah,
See you
yeah.
later.
I'll come in here, after third.
Appreciate it. Hey.
Would I be able to get the for the new packet for this one?
Oh, yeah. Pick that up yesterday.